Hello everyone, thank you very much for watching this video. My name is Mohammed Tanveer and I'm a staff software engineer at Codeplay, where I'm the technical lead for the machine learning libraries related work as part of the R&D division. In this talk, I'm going to explain how SYCL can provide cross-platform performance portability with little to no changes to the actual kernel. I'll explain how we can achieve acceptable performance with SYCL as compared to vendor-specific libraries. I will use deep learning as an example and use SYCL-DNN, our SYCL-based neural network acceleration library, to benchmark the performance of our SYCL code across a variety of different hardware platforms. I will first cover the most common challenges that we face with running deep learning models due to the lack of a common framework across hardware from different vendors. Then, I will define the characteristics of an ideal solution for performance portability by formulating the problem statement. Afterwards, I will explain how our contributions to the SYCL standard help provide performance portability, followed by some performance evaluations. Then, I will briefly touch how we were able to provide end-to-end support for deploying SYCL code on RISC-V architectures, and then conclude the presentation. There is a wide range of tools and frameworks available for the development and deployment of deep learning models. All these frameworks have their own benefits and limitations due to the variation in their core design. One framework may support some optimizations while the other may not. So it is slightly difficult to choose which framework to use. This also means that migrating between frameworks to meet the target hardware's requirements can be a problem. Many vendor-specific libraries attached to high-level frameworks like TensorFlow, PyTorch, etc. are usually closed source and require proper versioning for correct usage. Most hardware vendors provide hard-coded implementations of inference engines implementing the same neural network algorithms for a certain hardware, and that the same engine may not work for the hardware from any other vendor. Thus, having an abundance of these hardware-specific engines implementing the same neural networks creates a redundancy since all the code bases are primarily implementing the same application. All of these problems are fixed using the Open Neural Network Exchange framework, the ONNX framework, and its corresponding runtime that implements the ONNX specification, the ONNX runtime, except the code redundancy issue which still remains. ONNX and ONNX Runtime are a few open source projects that have been initiated by some tech giants to mitigate the diversity in the technologies, all while promoting model migration and maintaining comparable performance. ONNX creates a unified platform for all frameworks to translate their models into an intermediate format and then either load it into some other framework or use this intermediate format to run the model over a diverse hardware set. This is done using the different vendor-specific execution providers supported by ONNX Runtime. But without the presence of a unified cross-platform portable backend, we cannot remove the code redundancy. So an ideal solution to solve this problem would need to be portable, maintainable, and performant across different hardwares. The SYCL standard aims to be portable across different platforms like Intel CPU, GPU, NVIDIA GPU, and AMD GPU, to name a few, due to a wide range of SYCL-based implementations available. SYCL is also maintainable since all the latest and legacy code releases are open source and can be accessed publicly. However, there are concerns among the community about the performance of the same SYCL code on different hardware. I will now address how we at Codeplay have tried to tackle this problem to put these concerns to ease. SYCL is based on the modern C++, and to minimize the redundant code, we make use of the template metaprogramming to write highly parameterized kernels. We only do this for the most compute-intensive parts of our code, following the Pareto principle, which basically says that 80% of the performance rests with only 20% of the code. So if we are able to optimize this 20% of the code, we should be able to see significant performance improvements. Thus, we write these templated kernels and fine-tune them based on the target hardware to yield most optimal performance. This allows us to reuse the same kernel code across the device of our choosing. We need to make educated choices on the type of template arguments to use, since they will dictate the maximum amount of performance we can extract from the code on any hardware. We parameterize our critical code blocks with metrics like cache line size, workgroup size, local range size, etc. We mix and match a bunch of different combinations of these parameters to see which configuration best fits the underlying hardware. Based on our experience, we have come to the conclusion that having the acceptability criteria for portable performance between 70 to 80% of the vendor optimized code is reasonable. Our SYCL-based neural network acceleration and BLAST libraries are built with focus on the performance portability, and we use these interchangeably to get the best performance on the target hardware. Moving over to the performance evaluations, we first need to identify the compute-intensive blocks in our application, the neural networks. Then, we need to choose the target hardware, tune the compute-intensive code for that hardware, and then evaluate performance. This process is repeated for every target hardware. For the sake of this evaluation, I will refer to the VGG16 neural network model as an example. VGG16 is widely used for image classification applications. It has a bunch of convolution layers with a few pooling and activation layers in between, followed by a few fully connected layers and a softmax layer at the end. Our SYCL-based implementations for all of these operators reveal that the most compute-intensive block for VGG16 or any other similar neural network model is the GEM operation. Almost all convolution implementations in SYCL-DNN end up calling GEM, and the fully connected layers are also implemented using GEM. So this operator contributes the biggest chunk in performance for running neural network models using SYCL-DNN, and we can get significant performance improvements if we can fine-tune this operator for the target hardware. Now I'll first discuss the tuning for the Intel hardware. We choose the i7-6700K CPU and the HD Graphics 6530 for the GPU and use these for the evaluations. We opt for a machine learning based tuning methodology for the GEM operator as suggested in this paper mentioned here, which basically provides the most optimal GEM configurations for the above mentioned Intel CPU and GPU for the VGG16 model. The use of C++ templates with tuning creates a paradox where we have to strike a balance between the required performance and the library size. Tuning each layer of the neural network individually would yield the best performance. But for bigger, more bulkier neural network models with a lot more layers, for example, GoogleNet, having one tuned GEM kernel per layer will increase the size of the library significantly. On the flip side, we can tune the entire neural network model and get a single tuned gem per neural network model. This would obviously be slightly less performant, but it would keep the library size in check. For the course of this evaluation, we opt for the semi-optimal tuning regime, which basically means that we tune the entire neural network model and get a single tuned gem kernel for that particular hardware for the VGG16 model. The results on the Intel hardware reflect that the tuned version of SYCL-DNN is more performant than its non-tuned counterpart on both the Intel CPU and the GPU. We compared the performance against one DNN-based implementation of VGG16 and see that on the Intel CPU, our code performs better than the one DNN implementation, whereas on the GPU, our code is within the acceptability criteria of the one DNN-based implementation. Thus, our SYCL-DNN-based VGG is either better or lies in the acceptable performance range of one DNN, which advocates the cross-platform portability of our code on the Intel hardware. Next, we extend our code to support NVIDIA hardware. DPC++, the SYCL implementation from Intel, provides support for running SYCL on CUDA-enabled devices by mapping the SYCL instructions to the corresponding PTX instructions. Using DPC++ as the compiler allowed us to run the same SYCL-DNN code on the NVIDIA GPU as well. The target device chosen for this analysis is the Titan RTX. SYCL BLAS, our BLAS library based on SYCL, offers an auto-tuner tool which tunes individual gem operators for each layer of the model. We modify this tuner to perform the tuning over the entire neural network model in line with the semi-optimal tuning regime to get a single tuned gem kernel. We tune the entire neural network model by processing the VGG16 model against all the feasible gem configurations at our disposal, and then measuring performance for each case. Once the tuner finishes, we perform a post-processing step to report the best performing gem configuration for the VGG16 model on that particular hardware. We compared the performance of SYCL-DNN code against a pure cuDNN-based implementation of VGG16. Here again, we can see that the tuned SYCL-DNN code performs much better than its non-tuned counterpart, and that it is within the acceptable performance range of the cuDNN code's performance on the Titan RTX. Now, I'll demonstrate how we can run the same SYCL-DNN code on the RISC-V simulator, opening up a ton of new and exciting design opportunities. As per our knowledge, there is no framework out there that provides full support for the RISC-V architectures. So I'll take some time to explain how our tools can be used for providing end-to-end support for neural networks on RISC-V architectures. We use the Spike simulator for this analysis, and we make use of CodePlay's Akron platform for the end-to-end deployment of SYCL code on the simulator. Nowadays, domain-specific accelerators are essential to get the most effective performance on chip. The chip's design needs to be tuned properly to cater the requirements of the target application, in this case, the neural networks. The RISC-V architecture provides a minimal baseline instruction set and is flexible enough to integrate custom extensions. A big number of companies have started looking into RISC-V architectures to cater the requirements of their own specific application, may it be autonomous vehicles, industrial automations, to name a few. Designing custom chips using RISC-V is a hot area these days, and the design can benefit from the vector extensions supported by the architecture and help achieve high compute density on the chip. The Akron platform provides a top-to-bottom software stack which helps deploying SYCL code on the RISC-V or some other heterogeneous hardware. We use a variety of our tools from the SYCL ecosystem, including Compute CPP, Compute AOTA, SYCL-DNN, SYCL Blast, etc., to accelerate SYCL code on RISC-V. All of these tools sit on top of our SYCL implementation stack, and by providing them to the compute mux, we generate an API for hardware vendors to implement the entire Akron stack on their hardware toolchain, and then that can be used to generate custom instruction set for that particular hardware. I'll give a brief overview of how the Akron platform deploys a kernel like gem on the RISC-V simulator and explain the steps involved. On the left-hand side of your screen, you can see an example gem implementation, and the main computation block within this code basically has a nested loop to perform the gem operation as shown on the right-hand side. The device compiler captures the SYCL kernel code and creates a scalar LLVM intermediate representation out of it. This intermediate representation is then translated into the SPARE-V instructions using the device compiler. These instructions are then fed to our vectorizer, which converts them into vector intermediate representations instructions. These instructions then go through the LLVM backend and get deployed on the RISC-V cores. To give a brief taste of things, here is a demo video for image classification with VGG16 on the RISC-V Spike simulator. This is the command that we use to run the VGG model using SYCL-DNN. The code is supposed to classify this dog from the ImageNet dataset, and it does so by giving out the proper name for that particular breed of the dog and the proper class number as well from the ImageNet dataset. And this entire thing is working on the is running on the RISC-V simulator. To conclude, our SYCL-based libraries for neural network operations and BLAST can be a good start for achieving performance portability on different hardware using the same code. Our Akron platform also provides a complete stack to deploy SYCL code on any custom heterogeneous hardware. A pre-built package for the deployment of VGG16 on RISC-V using the Akron platform is now available on our website on the link provided here. I would also like to take this opportunity to announce that the basic skeleton for adding SYCL execution provided to the Onyx runtime is now complete, and the code is available publicly on GitHub. We currently have support for the most common neural network models including VGG16 and ResNet50. Feel free to try out the code and provide feedback. Thank you for listening to this talk. Unfortunately, since it's a recorded video, I can't take any questions right now, but I will be available on Slack and through the email mentioned here. Feel free to reach out over Slack or over this email if in case you need any more information or if you have any questions regarding the work that was presented in this presentation. Again, thank you very much for your time.